Okay, good afternoon. It's my great pleasure to have you all attend another in the series of Looking Back. So this is looking back. So Reji will be looking back on a immensely successful and fruitful career at RRI, and we will all look forward to what he has in front of him. He's got a lot of interesting challenges ahead, and so let me say a few words. Reji has been at RRI for over 25 years, and he did his PhD from QSAT and worked at RRCAT Indore, which I didn't know actually, so that's interesting. And then proceeded to the University of Regensburg, Germany, for postdoctoral research, and then he was at TIFR, which the years that Ravi mentioned in his talk, and then joined RRI as a faculty member. So he worked on laser-generated plasmas, ultra-fast spectroscopy, nanostructuring with intense laser pulses, and nonlinear optical properties of various materials, novel materials. He has authored over 250 research articles in international journals, holds 2 patents, and contributed to 3 book chapters. He, of course, has mentored several postdocs, PhD students, and master's project students, many of who are probably also part of this national conference that we are, hosting at RRI. And he has been, to me, immense source of strength, because when I came into the institute, there was a situation where I didn't know, how to get things done. And Reji stood by and stood up to many of the tasks that needed to be done. And I remain very grateful to his unstinted support for many of the things he did. And I hope people appreciate or will learn to appreciate that that was a great contribution to the institution. I mean, that is the part I am aware of. Of course, I'm sure, many of the students would remember their, the mark you left on their careers and, how you helped them. So let me invite Reji to sort of deliver his looking back talk, which is Light Matters, Reminiscence of a Career in Science. Reji.
Thank you so much. Am I audible to this? You can hear me? Okay. Thanks a lot, Tarun, for the very, very kind words. So, and thank you all for coming. And I also thank my students who organized this conference. It was a lot of work, I know that. And I should thank Subbu for being behind everything. I mean, not just the conference, but many other things where we work together. Well, I'll come to that later. So today in this talk, it is a looking back talk. So there are a lot of things to remember. So I think I won't be saying much science. I mean, there'll be a little bit of science which is inevitable because that was my career. But otherwise, there are so many things to remember and so many things to say, but which I don't think there is enough time for that. Whatever is possible, I would like to tell you about myself a little bit, since when my memories start. So in the beginning, there was light. This everybody knows. Yeah, a lot of light. And so as I said, my oldest memory, anything that I remember for the first time, is of sitting under a light, an incandescent light.
Not a lamppost.
Not a lamppost, no. It was, luckily, I mean, we had electricity at home, and it was a light in the house itself, yeah. So, and, in those days, I'm talking about 1965, that was when I was born. And many places did not have electricity at that time, but we had, fortunately. So, under an incandescent lamp, and then, intently looking at a spinning top. So this is what I remember. My earliest memory is this. My parents are close to me. And in 1986, you study Goldstein, so the motion of a spinning top in classical mechanics. So as described by Goldstein, it involves Euler's equations, and these equations describe how the top's orientation changes over time. So that was something that happened in 1986. So my schooling was in a Jesuit father's school. So they don't take disobedience very lightly. The school was very strict, and it was very good also. I mean, now when I look back, I think that kind of strictness was okay for me, okay for some of us. But in these days, that is not necessarily the norm. And the first headmaster that I remember, Father Joseph Manchil, he had a video camera in those days. It's something which is very, very unusual. And then we had Father Philip Thail as the next headmaster. And this is my school where I studied. And this area that I come from in Kerala is the place where we mostly cultivate rubber. So that is the rubber belt of Kerala. And this was a source of income for most people there. And almost everybody had a few rubber trees in their compound. And then you have to tap it, you get the sap like that. So all the rubber stuff that we use, that we wear, everything, this is the very, very primary stuff from which all that is made. And we had a teacher, particularly remember, who taught us math in the 8th grade. He was an expert in punishing us, and as a result of that, all of us became experts in trigonometry. So that was the end result of that. So for college, I went to KE College, Mandanam, near Kottayam, and then followed by the University of Cochin. So pre-degree BSc there. I wanted to be a scientist, but then didn't have much clue as to how to go about it, because these are practically villages, and you hardly see a scientist on the road in those days. And so what happened was I had some difficulty to get into an MSc admission because of my habit of studying things only at the last moment. I had to skip. I had no choice but to skip something in the math paper, and I decided I will skip analytical geometry. And because of that, I lost 20 marks. See, almost everybody in the class got 200 out of 200 when I got 180 out of 200. This was really a problem because I could not, it was very difficult to get into a college for MSc because in those days, the seats for MSc were so limited, like, 4 seats, 5 seats. That's the kind of seats you had in the colleges nearby. But fortunately, Cochin University had 16 seats. So I got in as the 12th guy in that list. So Professor Rekupadi actually advised me to apply to the University of Cochin, and now it is CUSAT. So when we were halfway through MSc, it became CUSAT, Cochin University of Science and Technology. And my application was late by 2 days. Fortunately, the head of the department, the section officer actually turned me back. When I reached the university with my application, the section officer said, "You are late by 2 days, boy. Go back. I can't take this." At that moment, the HOD rang the bell and he went to HOD's office. And by chance, he told the HOD that there's a boy who came with an application form. I sent him back because it's 2 days. Professor Krishnapillai said, "Call him back. Let us take the application." So I was like, some 300 meters away from the physics department. I was in front of the math department there. Those of you who know CUSAT will know where exactly I was. Then the attendant came and called me from behind and asked me to go back and submit my application to the HOD. And then I got in for the MSc. So anyway, and that was when the department decided to start quantum electronics specialization. So we had Professor K. Babu Joseph and Professor B.P.N. Namburi as teachers for teaching us quantum electronics. This actually helped me later because at the MSc level itself, we studied laser physics, optoelectronics and things like that, which was pretty useful. And then proceeding to the doctoral degree, so the title of my thesis is nonlinear optical properties of selected laser dyes investigated using photoacoustics, fluorescence, and stimulated scattering. So along with two other students, Padmaja and Sadi Menon, I got selected as JRF in a DST project on laser spectroscopy. And then Professor C.P. Girija Vallavan, V.P.N. Nampuri, and Jacob Philip were the investigators. So the photos are here. And I was advised to work in the area of photoacoustic Raman spectroscopy. So the connection with the Raman is happening from early enough. But eventually I did not do parts. The purpose was trace detection of gases. But I ended up doing photoacoustics, not spectroscopy actually, because I worked only at two wavelengths, which was available there. The pulsed Nd:YAG laser, fundamental at 1064 nanometers and 532 nanometers. So it's not truly spectroscopy. But we looked at the nonlinear optical properties of various materials just by using those two wavelengths. And in addition to that, fluorescence was done and stimulated scattering, stimulated Raman scattering and stimulated Brillouin scattering. These were done. So two photon and excited state absorption, nonlinear fluorescence. So these things were studied. And I'm very proud of my academic pedigree, which connects me to Professor Raman in this fashion. So I'm here at the end of the chain, and then my thesis advisor, Professor Jacob Philip, he's not related to me, by the way. His thesis advisor was Professor K.S. Vishwanathan, who was Raman's student himself. And Professor Vishwanathan actually is the founder of the physics department of Kerala University. And so this is my connection to the Raman Research Institute even before I came here. So now, my first encounter with pulsed light. Throughout my career, I used mostly pulse lasers. CW lasers, of course, but it was much limited in comparison. So that happened with, when Professor Namburi actually told me about doing parts, he actually gave me this paper also. It's a seminal paper on pulsed photoacoustic spectroscopy. So in those days, it was called optoacoustic spectroscopy of condensed matter, written by C.K.N. Patel and A.C. Tam. So C.K.N. Patel, I'm sure many of you will know as the inventor of the carbon dioxide laser. So he was working in the Bell Labs. So in this paper, this is where I really started my work. So the idea is very simple. You can send a laser beam into a sample, and then if the sample absorbs, there will be some heat there. So the medium will expand locally, and then there will be an acoustic wave. So you can detect, if you can detect the acoustic wave, then it can be shown that the amplitude of the acoustic wave is proportional to the absorption that happened. So it's a very simple relationship, easily derivable relationship. So that was the idea. And then, so that means now you have to make some device to really, detect sound. So the paper actually gave all those details, like how to make that transducer. So this is made in steel, and you have a piezoelectric detector here. That's a small cylinder, a PZT cylinder there. Then there's a Teflon ring around that. Then a piece of lead, copper, a spring, and then it is connected like that. So there are grooves here so that you can actually, really turn it and fix it into a cell. If the pitch is sufficiently tight, then you can make it leak proof. So that's what we did. So we actually made a very similar, this is given in the article. So we made it almost replicated, almost the same way, and then started setting up this experiment. So there is a photoacoustic cell, you have the transducer screwed onto that, and then you have, turned and fixed into that, and then you take your sample. I ended up using liquids because you have to think about acoustic impedance matching and all that. If you are going to work with gases, you have to use microphones. So we used to have very, very small microphones, electret microphones for that. So there was another student who worked on gases. So he used very small electret microphones. But I had to use these transducers. So then we ran that experiment. Even though we had a dye laser at that time, we had one, but I used only the pulsed ND-arc laser. And then the signal could be detected. In some cases, if the absorption was very weak, then we had to use an amplifier. So the paper actually gave the design of an amplifier also, an audio amplifier. I mean, it has to be ultrasonic amplifier. But those ICs were not available in India at that time. So we designed, one of my seniors, a PhD student, who eventually became a professor of instrumentation. This is Professor Joni Isaac. He actually helped me with designing an amplifier using the very common transistor 2N2222. So that was sufficient for our application. And it could go up to something like 10 megahertz. The frequency response was up to that, and that was enough for our measurements. That's the way we started measuring. And this is how the acoustic signal will look on an oscilloscope. You need only a very, very small 100 megahertz oscilloscope is sufficient for this, because you are not looking into the time aspect, you are only looking at the amplitude of this. And we actually had boxcar also. So in those days, it was just before the averaging oscilloscopes were coming. So at least we did not have one, but we had a boxcar. So this was interesting. So used the boxcar gate, fixed it to that position. This is where you need to measure. And then we could measure properly these signals. So once you start getting your acoustic signals, there are various things you can do with it. Like, for example, a very simple experiment is to measure the ultrasonic velocity in a liquid. So you can just, use the same cell. Let's say you take toluene, put it in that, see where the signal comes. So you know where your laser is. So this is your laser pulse. Use a photodiode for getting that laser pulse. And then just look at where the acoustic signal comes. Simple calculation, you get the velocity of sound through this. So people could actually find out the velocity of various. I think that was my very first paper for a conference. So which probably happened in BHU, I think, or no, NPL Delhi actually. So in the Acoustical Society of India, there is a journal like that. So it even got published in the Acoustical Society of India.
Can you hear the light?
Yeah, it was like hearing light. Yeah, we were literally hearing light. So all those little things were done. So this is one spectrum from literature, which actually shows the power of the technique. So you can see that this is the absorption spectrum of water, and spectrum of water in the visible spectral region, 4,000 to 7,000 angstroms. So normally, if you take some water and allow light to pass through, it just passes through. It's very difficult to measure the absorption on a typical UV-based spectrophotometer, for instance. But this one, the photoacoustic technique, can really measure that. And you can see it, this is how it goes. So this shows the sensitivity of the experiment. And therefore, I didn't really have any signal to noise issues, because most of my measurements had sufficient signal. Anyway, you have a boxcar. And into the second year of my PhD or something, we got averaging oscilloscopes. That was enough. Because in an averaging oscilloscope, you can really measure a signal very clearly, even if it's only 2 millivolts. That was a kind of limit which I experienced at that time. So this was good enough. Now, so after my PhD, so I had this short stay in RRCAT indoor. So it was a permanent position, in fact, appointed as, they were taking some people external to the training school. So I got in through one of those calls as scientific officer SD. This was way back in 1994. So Kailash Rustagi and SM Mok were my bosses. But I stayed only for 6 months. They were like, first of all, it was extremely hot when I went there, and I was quite used to the reasonably better, weather of Kerala. And this was something, that heat I just could not stand. And, you get totally dehydrated. And I was staying in the second floor of a building. And in the evening, when I come back, literally I could not climb the stairs. Somebody had to help me. I was so tired. So I thought this is not going to work for me. So now I'm looking back, maybe if I had stayed for, let's say, 1 year or something, I would have got adjusted to it. But that time, I'm in young age and all that. And that's when I got an offer from Germany for a postdoc. And that happened because we had at the very first SERB school on ultra-fast phenomena was held in 1993 in Dharwad, Karnataka University. So some of us, we were all PhD students, many people from different universities in the country. Eventually what happened was all of those people, we are still friends. We were all PhD students at that time. Some of them became vice chancellors, some of them became big scientists, everything happened. Very few of them actually left science. So this meeting, in that meeting, my postdoc mentor, he was a speaker for something, Penskoffer was there for 2 weeks, and he stayed all the 2 weeks, very unusual for him. And I had that connection with him at that time. So because he was working exactly in DICE and all, we had a lot of conversations. So I had requested him for a postdoc position, which came through after 6 months or 8 months. And so that's when I decided to quit RRCAT and move to that position. So this is my first postdoc mentor, Professor Alphonse Penskoffer. He was an expert in nonlinear optics, ultra-fast spectroscopy, and high-intensity Raman interaction. So he has written one solid paper on high-intensity Raman interactions, which is cited so much. Almost everybody who works on stimulated Raman and things like that, they read that paper. Very good paper. And in fact, my work there, by the way, even though he was using picosecond lasers, femtosecond systems he had, home-built actually, because he was from the school of Wolfgang Kaiser. So Kaiser was a big name in Germany because he is considered by many people as the father of laser physics in Germany. So he was in Bell Labs, and just a few weeks after Meyman demonstrated the first ruby laser, actually Kaiser and his team demonstrated again their ruby laser, which had much better directionality. So they missed getting a Nobel Prize or anything just by a few weeks, but eventually he returned. And in 1961, just 1 year after the laser was invented, the same team, Kaiser and Garrett, they discovered two-photon absorption. So two-photon absorption induced fluorescence. So then he returned to Germany. So he was in Purdue, in US Army Labs, Bell Labs, and then in Technical University of Munich, where many people like Alphonse Penskoffer became his co-workers and earned their PhD degrees. So this, in fact, Kailash Rustahi has written, very accidentally, I got this paper written by Kailash. So this appeared in Physics News in 2020, and he writes about nonlinear optics, and that's where I got his photo from. I was actually looking for his photo. Then I got this. So I took the photo and also read the paper. So there, he actually mentions meeting a few of people, including Alphonse, in the Gordon Research Conference in Santa Barbara in 1974. Then I remembered something else. Memories are long. Kailash had come to Regensburg when I was there. So all of us went for lunch together. And at that time, he actually asked Penskoffer, do you remember that we had met in Santa Barbara in 1974? I remembered that when I read this. So that was the way things are. And then, Regensburg is very close to Munich. By train, it is 1.5 hours. And, the Bavarian Alps is nearby. And so these weekends were very good. So my German students, friends, actually gave me one warning as soon as I landed up in Regensburg. Don't go to the university on Saturdays. If you go once, then Penskoffer will never, he will ask you to come every Saturday. So don't show your face on Saturdays there. Sundays are okay, anyway, nobody expects you to be. So I followed that advice. The very first Saturday, I disappeared from the university. But then on other days, it was very, I had a lot of work. Like you start at 8:30 in the morning. Usually I left the university at say 10 o'clock in the night, 10:30. And I still remember one of those winters, which was particularly harsh. I had to walk for half an hour to the apartment, which was graciously given to me by Penskoffer himself. It was his own apartment. He gave it to me for a very small sum of 50 Deutschmarks per month. That was very nominal charge he charged. And so one particular night, it was very cold, so I was walking, multiple pieces of dress and all that. So there's a weather station on the way. This is meter on the road. So when I checked the temperature, it was minus 22 degrees Celsius. So I was walking through minus 22 degrees Celsius for half an hour. When you walk like that, when you reach your home, there will be ice on the eyebrows. Wherever there is, something, ice will form. So there will be on the eyebrows, there will be ice. It was like that. Anyway, so the good thing was the Alps was there, and you could go have treks there very often. And we also had that time in Germany, because nobody was traveling in the trains. So everybody has a car. So the government, actually that ministry introduced something they call Wochenende ticket. That means weekend ticket. So a group of 5 people can travel anywhere in Germany from Friday night to Sunday night just by paying 5 Deutschmarks. So Deutschmark was the earlier currency before the euro. So then all the trains were full. So you can take this, and people used to sell the tickets, You travel for one day and then sell that ticket for 3 Deutschmarks to other people. So all those things were happening there. And anyway, so that was it. Well, so I came back after my postdocing, and then there was a break from research. So I taught for 2 years at this place called the Sacred Heart College in Tevera. It's in Cochin. It's a well-known college there. So I had to give classes to, the present day plus 2. In those days, plus 2 was in the college. So it was called pre-degree. So I had to teach, if this hour I am teaching in pre-degree, the next hour I'll be teaching in MSc. So we had MSc there. So it was interesting. Only thing is the pre-degree classes had like 90 or 100 students. And there were no mics in those days, It was impossible to. And the moment I landed there, I was made class teacher for one pre-degree class. Can you imagine my situation? Anyway, so I was away from research for 2 years when I received a life-changing phone call from someone. GRK. I don't know whether you remember that. You do. GRK called me on the landline to the physics department of Sacred Heart College, because Reji was looking for someone for some of the NLO experiments, and he came to know from Professor Girija Vallam, and that's what I heard, in Kusat, that there is a guy here, he is teaching in a college, but he had worked with Penskoffer. So I think that's what made Reji call me on that phone, and then we spoke to each other. So Reji asked me, would you like to come? You have to, if you come, we can work together for some time. Of course, you have to apply for a postdoc position and go through the formalities like interview and all that. So I thought, okay, it's a good opportunity to come back to research. So I made the application. I went there and gave the talk. And eventually, anyway, I was accepted. So started working together with Reji in TIFR. So Reji introduced me to the C-scan technique. The morning also we have heard from Reji himself about C-scan, and also from some of the other speakers, the conference, what C-scan is. So I won't discuss this much further. It is widely used nowadays for the determination of absorptive and refractive nonlinearities in materials. So we worked on metal nanoparticles, that paper which you talked about, and organometallic complexes, which were given by IIT Bombay colleagues. So, and we wrote a few papers together. So this is a C-scan. I think I don't really, many people know. Basically what it does, see this experiment, here what is done is you change the intensity or energy density of a laser beam, of a light beam, and then measure the transmission or the refractive index of the material which is being irradiated. So one easy way to do this is to send the beam through a lens, then move your sample in the focal region. So at the focus you have maximum intensity, and as move the sample a little bit towards this side or that side, the intensity changes. So you can measure the intensity dependent transmission. Now if you put an aperture in front of the detector, then it is possible for you to measure the nonlinear refractive index and how the refractive index changes. So then you can, the equations pertaining to this are alpha is equal to alpha naught plus beta I, where beta can be a coefficient for the excited state absorption, or it can be a coefficient for two photon absorption. In some cases, it could be a coefficient that represents the scattering in the system. So similarly, we can write n is equal to n0 plus n2i. So this experiment I started doing for the first time with Ravi's suggestion in TAFR in the lab there. So this is the paper Ravi spoke about today morning. So this was, as you said, we communicated that just, 1 week before I came over to RRI, and it was very well received by the community. So this is a paper in Physical Review B. So the samples for this metal nanoparticles were given by T. Pradeep from IIT Madras, and Sandhya, who was a student, she was a PhD student at that time, she eventually became a professor in NIT Calicut. So she is a professor there now. So this was the first time, to the best of my knowledge, that ever somebody observed humps in the C-scan. Because if you look at the theoretical curve here, which accounts only for nonlinear absorption in the nonlinear positive absorption, that is, an optical limiting kind of situation, you will not see any humps there. But if you look at this data, you can see humps there. What it actually means is that in those intensities, those are it's a certain region of intensity. There, the material transmits more. But as you increase the intensity even further, that is when you go to the central focal point, it decreases. So initially there is an increase, then there is a decrease. So this kind of a behavior, actually nobody has, I checked later. Many papers, I could not find anything actually. So ours was the very first report of this kind of a behavior. And later on, it became clear that, what are the reasons for this? It was a saturation of the absorption. So colleagues in Atmol, in TAFR, Deepak Mathur, Professor Mathur was there. Then M. Krishnamurthy, now he is in TAFR Hyderabad, and Debu Goswami in IIT Kanpur. Reju, he is still in CUSAT, he is a faculty member in CUSAT Physics Department. Far, Firoz Rajkara was there, engineer. Vinod Kumarappan is in Kansas State, and Ravi Bhardwaj and Vijay Lakshmi, they are in Ottawa. Sudeep Banerjee, he is also in the US. So we were we were in one lab. Now from there, I am coming to RRI because ERK suggested I apply to research institutions, because normally I would have, even though I came to TAFR for 1 year, so I was encouraged to continue for 1 more year. So after almost finishing 2 years, then I was told, do you really want to go back to the college and teach there? Why don't you apply to research institutions? So I made a few applications. So got selected in Kiel University in UK as a research scientist and also in RRI on successive days. On the previous day, I got information from Kiel, and on the next day, I got information from RRI about selection. So I didn't know what to do for some time because Kiel I had gone. I had personally gone for the interview. It's a small village. I liked the place very much. The people were very welcoming and all that. But they said it's a 5-year position. It's a contract position. So that's what, at that time, there is big secret which I didn't know. RRI also gives you a 5-year position. I didn't know that. RRI always gives you a 5-year position, even if you become professor too, I think. I don't know. I think that's that's changed.
5-year position.
Yeah. So somehow this was not very clear to me. Okay, in any case, even if it's a 5-year position, it's still in the country, and so maybe it's a little more secure. So I wrote back to Kiel saying that it so happens I got a position in Bangalore near my hometown. So the professor wrote back a long email. He wrote to me that we say it's a 5-year position, but for all practical purposes, you will become permanent. So he wrote all that, but eventually I decided I'll come to RRI. So and then it was Professor Kumar, our director at that time, Professor N. Kumar. He was the director. Actually, he processed my application and he invited me for the talk here, everything. Then Hema was there as she was the very first faculty member in the LAMP group. So in those days, we were known as optics group. It was not LAMP group. The name LAMP was given by Kumar. The way it happened was, one fine morning, we saw Kumar running towards our building. He was like, when he gets excited, he is very excited. Anuja knows that, right? So he came and told us, I found a new name for your department, for your group. So Hema and I, so which name? LAMP, he said. LAMP. So yeah, light and matter physics. He got inspired from the same name in some European lab, actually. So he was traveling, he found this LAMP there. So he thought, this is the right name for you. There was also another reason for it. Some people had started writing emails to Hema or me saying that they want to work with some lenses, mirrors and all that because we are an optics group, so the optics that you study in college is about lenses and mirrors and all that, prisms. So it was also necessary that, this misconception had to be cleared. So we accepted wholeheartedly the name LAMP. And later on, Meena was there already and Andal was a postdoc that time. So then Sadik, Urbashi, Saptarshi, Sanjukta and Smijesh joined the LAMP group in subsequent years. Andal joined after I joined. Now there are 3 people I am very much indebted to in RRI. Revi Subramanian was of course many of you know Revi, he was the director after Kumar. Revi was very supportive to me, so all my work, research work, whenever I wanted something, he was very, very supportive about that. So we had a good relationship. Then Rad, of course. In fact, I never had much of an interaction with Rad. I think I've spoken to Rad only for maybe 5 or 6 times. That was all my interaction. But whenever there was some discussion, it was very, very inspiring. So therefore, he was a kind of person. Those who know Rad, you all know how he was. Very inspiring person and very thankful to Tarun. Because when Tarun joined, in fact, Tarun gave me a lot of administrative responsibility. I wouldn't say a lot, but a few. But it was a bit different from all the science that you normally do. This actually allowed me to, to deal with people, to improve those skills. Because any kind of administration requires that you deal with people. It is man management. So the opportunity that Tarun gave me for that purpose, like, the coursework committee was there. Engineer was with me all the time. You are there? Yeah, full support Engineer gave me regarding the coursework. Then, the RPF coordinator position, now Arun is the RPF coordinator. So these things were very, very useful even for me, even after my retirement. That helped me a lot. So now regarding work, so I was mostly with nonlinear optics in that regime, the perturbative regime of light matter interaction, where you deal with bound electrons, the perturbative behavior of the bound electrons, Chi2 processes, Chi3 processes, things like that. And then we also entered the soft ablation regime with structuring with Nancy and Anoop. So we did that. So Nancy's thesis is basically surface structuring with light. And strong field, of course, we never went to. That's a regime of Reji and high harmonic generation, Svijesh will be doing. Sub-femtosecond X-ray and electron pulses, attosecond pulses will be done here in future. Hard X-rays, multi-MeV electrons and all that, I don't know what is the plan for that. So this is the intensity scales at which all these different processes happen. So I worked in, when I say I, that of course means the lab, all my students, even project students, visiting students, all that. Nonlinear optical behavior of novel materials, which was a continuation of what I was doing in TAFR for 2 years. Then laser produced plasmas, generation and characterization, and surface structuring using exotic laser beams. So we bought these lasers in the year 2000. So this was the femtosecond system. It produces very, very short pulses, like 100 femtosecond pulses. That's the time width. And in Bangalore, at that time, there was no other femtosecond system. Even in IAC, it was not there. We were the first people to get it. And Reji came all the way from TAFR to RRI at the time of the installation. So because the engineers had to come and install the system, we were all very new to it. So this is the, its name is Tsunami. Actually, that's the name of this model. And 100 femtosecond pulses at, model locked pulses at 82 megahertz, 500 milliwatt power at 800 nanometer. And this laser is used for amplifying the pulses that come from here. So we have this laser amplifier. So we had the oscillator as well as the amplifier. So with the amplifier, it was possible to get 10 millijoule energy at the output. Only thing is, the only limitation is that at that time, my options were I could go for a 1 millijoule system which ran at 1 kilohertz. The other option was to go for 10 hertz and get 10 times the energy. So because I was fascinated by all the plasma work Reji was doing, Reji and his students were doing in TAFR, so I went for higher energy. So the pulse repetition rate went down, but it was fine, it was okay. Only thing is, some of the experiments will take more time, but it is fine. Students are willing to work hard into the night, so it is okay. So these systems came, and these were purchased with a generous fund allocation by Professor N. Kumar, because in 2000, it costed us 1.3 crores, which was big money at that time. So this is, I will briefly go through what we did in the nonlinear optical measurement of materials. So many of them are here, sitting today here. They all worked in various times. Like I have to start from year 2000. Anija was my very first PhD student, followed by Sandeep. And Anija came to me as a VSP actually, both Anija and Divya. I was very new. I had just joined, and maybe 3 or 4 months into my stay in RRI, she came and asked me, and Divya also was with you, I think. I don't know whether you came together or separately. So both of them wanted to be VSPs, and I happily took them because I'm having nobody. I need some students anyway. So took them, and eventually Anija continued with me for PhD, and Divya joined Hema for PhD. And so then, of course, others came. Jindo was here for 2 years. So like that, all of them. Basically, I mean, we are looking at molecules. In those days, we are looking mostly at organic molecules. So these can be modeled by a 5-level model, where you have a singlet ground state, and there are excited states. There are triplet states also. So the transitions which happen between these levels will define the refractive index to some extent, and also the absorption coefficient of the system. So that's what we were studying. So we worked in metal nanoparticles the same way we had worked in TAFR. So what is interesting about this is that for these nanoparticles, when you change the particle size, the color will change. So here you can see, this is not our paper, it's from somebody else, but then you can clearly see at 3 nanometer, this is the color. At 13 nanometer, it looks black, like that. So gold can look black at the right particle size. I am going to year 2012 because this is a paper which gave results one step, I mean, we went one step further in the sense that the TAFR study was on samples which had the same particle size. Here we worked on 3-4 different particle sizes. Another change was we worked with clusters. Clusters mean very, very small number of atoms of metals sitting together. That is a metallic cluster. So this happened when I was on a sabbatical in the University of Central Florida with Jane Thomas. And Rong Chao from Carnegie Mellon, he gave us the samples. And Panit was a student from Bangkok. So he was just starting his PhD. So we worked together. So what we did was, Rong Chao gave us these different clusters. 25 atoms of gold, 38 atoms of gold, 144 atoms of gold. So these are some magic numbers where they are stable. You cannot make an arbitrary number, take an arbitrary number and make a cluster. It won't be stable. But these numbers are stable. So he made them, he could make them. He was an expert in making these kind of very small clusters. Then to compare, we actually bought from Aldrich or somewhere plasmonic AU nanoparticles. Why we say plasmonic is because if the size is too small, then you don't see the plasmon band. It just does not support the surface plasmon band. So at 4 nanometer, you could barely see that, just like that. This is how the absorption looks at 4 nanometer. And this is the absorption of Ku25. You can see that when the number of atoms reduce like that, it starts showing molecular properties, like it behaves more or less like molecules. So that's why the absorption spectrum looks like that. So then we ran C-scan on all of these, and we could see very interesting results. So this was a result which kind of replicated to a little higher extreme level what we originally measured in TAFR in 2000. So you can see the saturation, but here the saturation is even more stronger than those measurements. And when we went back to the smaller AU25, it is like a perfect optical limit. So it was another validation of our thesis at that time, that the surface plasmon resonance is in fact responsible for the saturation that you see in these materials. I told you about the humps. The humps are the saturation. And that was related to the SPR. This was our conjecture. That's what we wrote there in that paper. And that was validated here. So this was one good result, and it got published in Nano Letters. Now again, this is coming back. When Kishore knew about this, he read these papers, and then Kishore said, aha, I'm also an expert in making these clusters. So he decided to make silver clusters. We wanted to try silver because let us see how it works. So he made AG9 quantum clusters. These were even smaller in number. And we studied them, and we got perfect optical limiting in them. Again, these don't have the SPR, and we see perfect optical limiting. The moment you start seeing the SPR, that's when you make your cluster bigger. When the cluster is big, it becomes a nanoparticle. When it becomes like that, you start seeing the SPR and its related transmission saturation. So this we published in JPhys MC in 2015. Now coming to another interesting work. So the routine C-scan is, now it is relatively easy. Frankly, I wouldn't say it is easy. The experimental setup is very, very easy, it will look like. But we always had some issue or the other. So it could take time to really make these measurements for various reasons. And anyway, now coming to the white light continuum C-scan. So this is a very different beast. So in the normal C-scan, you usually use only one wavelength. Your laser has just one wavelength. You measure at that wavelength. Maybe you measure at another wavelength. Now suppose you want to make a spectrum of the results, like how the nonlinear absorption varies as a function of the wavelength. If you want to do that, then either you should have a tunable laser, which we did not have. So by this time, the dye lasers were slowly getting out of the market. Now I don't know whether they are sold anymore. The OPA came instead, crystal-based second order nonlinearity. So those lasers are much more, they have much more tunability in the wavelength domain. So they are sold nowadays. So we did not have one. So we decided to adopt this technique, which was only a few papers, I would say only 3 or 4 papers had appeared in literature which use this technique. So what is done here is you have to use a femtosecond or a picosecond pulse. The pulse has to be very short. Now send that pulse to some medium. We found water to be very good. Water is enough, in fact. Focus that beam to water. Make a water cell. The advantage of water is that almost you can make a cell. We made 2-3 cells in the workshop, our workshop. Take a cylinder, a glass tube, fix 2 windows on either side using araldite or something, because it will withstand water. If you take acetone or something, it will immediately move away. I mean, you cannot really hold it. So water was good in that sense. We could easily make cells. Focus the beam, laser beam, into that water cell, and then you get white light. And this is very white. I mean, it's a photo of the white light that you get. So your monochromatic laser light is giving you very broadband white light. Now use that white light for your experiment. So you send the white light into your sample, and instead of using normal energy detectors for detecting the transmission, use a spectrometer for measuring the transmission. So you need 2 channels. One channel where you will measure the spectrum of white light. The other channel, your sample is sitting there and the light passes through, then you know the difference. Where did the absorption happen? So by this technique, and you needed a little bit of coding also to analyze the results. With that, Srikanth, Pranita and Priya, they wrote a paper in Applied Physics Letters in 2015. The sample used was reduced graphene oxide nanosheets. Graphene was very popular in those days. You do anything with graphene, you could publish it. That was the situation. But our work was not anything. Actually, this was very complicated. We published only one more paper because of the technical issues. Anyway, this paper got accepted very fast. And then it was followed by another paper, very similar technique, white light, by Binoy and Nivia. So that also appeared in Applied Physics Letters. Oh, this came before, 2013. It came before. Sorry, So here what was done, it was in coumarin. Coumarin is a dye, coumarin 120. So did those measurements, and we could actually replicate the absorption spectrum of the molecule by this technique. So then move on to another idea. So this idea occurred to me when I was on a sabbatical. So sometimes ideas come to you when you are away from your hometown. What suddenly occurred to me, I was in UMass Boston working with Professor Gopal Rao in his lab. He had invited me there. and I went on sabbatical. So in absorptive NLO, you see two kinds of materials. One is positive nonlinear absorption, the other is negative nonlinear absorption. Positive nonlinear absorber is called an RSA material, and negative is called an SA material. So saturable absorption and reverse saturable absorption. That is the term. For some reason, it suddenly occurred to me that what will happen if you keep a saturable absorber and a reverse saturable absorber in tandem, make a measurement, turn it around and make a measurement. So logically thinking, the transmission had to be non-reciprocal. Of course, I mean, we had to do the coding for that, and Anija did that. So in this paper, Anija wrote the program to ensure that this is the way it is. But before ensuring by calculation, I immediately did the measurement, because the reason was the following. While I was working with some color glass filters, there was one particular yellow color glass filter which turned out to be a very powerful saturable absorber. I was in fact trying to use that filter to cut down my green light energy in the laser, but when the filter went closer and closer to the focus, it started transmitting more, like the transmission went up. So it was very clear this is not a limiter, but it's a saturable absorber actually. So, and then there was a porphyrin solution. We mentioned porphyrin in the morning. They are very good RSA materials. So I took in a 1 millimeter cuvette porphyrin solution and just kept these two things together, the color glass filter and porphyrin together, kept them together with a piece of tape, cello tape, and put it in front of the laser, did a C scan, turned it around and did one more C scan. It was completely different. So this turned out to be a very interesting result. So we were actually seeing non-reciprocal transmission of light. So one step further, this will become an optical diode. If you want to make an optical diode, then there should not be any transmission in one direction. But we were still getting transmission, but like, at least one order down. So we said it is non-reciprocal transmission. And again, got this even, we were thinking of a patent, but I think eventually we did not go for that because of the cost involved. Brought this in 2007, and it was a very good paper. Then, Professor A.M. Rao from Clemson University, who was associated with Sri Sathya Sai Institute of Higher Learning in Puttaparthi, and Professor Sai Shivashankar Sai is from there, and Binoy, he is actually a PhD student, joint PhD student of myself and Professor Sai from there. So then he said, oh, now you have used materials which are 1 mm thick. Why don't we make it thinner? Let us make it mesoscopic. So he had multi-layer graphene, microns thickness, then C60 film, again microns. So now we put these things together. Now instead of 2 millimeter, it is like maybe 100 microns or something. And then we got very similar results. So it was working, irrespective of the size of, and it appeared in nanoletters. Then we also worked on with Jane when I was in UCF Orlando on another sabbatical. Earlier I showed the other work. So after doing that work, we devised this technique called OPAS, that is optical and photoacoustic C-scan. So here what you do is, normally you take one cuvette, put your sample there and do a C-scan. Now suppose you put that cuvette in a photoacoustic cell, and then this was the way it was all arranged. So the laser beam will fall like that, it will pass through, and through the other window it will go to a detector. So now if you move your sample cell, you will get a normal C-scan. But now if you put a transducer like that there, so you have to do a little bit of tweaking. So we had to really make it in such a way that we could turn the angle of the cuvette inside. So only at one particular angle where it directly faced the transducer, we got maximum signal. So then we arrest it there. And by doing this, we could see that, as expected, a signal that is complementary to the optical C-scan. So the photoacoustic C-scan was giving you a complementary signal to the optical C-scan. This was expected, but we proved it by this experiment. So that appeared again in APL in 2013. So these were some interesting experiments that we did in nonlinear optical measurements. Of course, we measured a lot of other materials also, but I'm not really going into any of them here. So this was the other activity of laser-produced plasmas. Started by Anija, so we made the big chamber because the original idea was to do this work. I mean, it was a bit, a bit ambitious for us at that time. Use capillaries for making liquid droplets, and then, irradiate those liquid droplets, and then measure the plasma. So we made a big chamber for that. We bought vacuum pumps and everything for that. So that was the way it started off, but eventually she did measure, but you measured X-rays, I think. Yeah, but that's what you measured in the end. So then all of these people have been associated with the NLO lab here, the UNO lab, and they all worked in plasmas at some point or the other. So what is a laser plasma spectrometer useful for? Nowadays, many of the space surveillance vehicles, those rovers and all, they have these kind of spectrometers inside. So there is a small laser sitting there. So let us say it moves to somewhere near a rock or some geographically interesting thing. You go there, you can shoot the laser pulse onto that, and then very sensitive cameras can detect the plasma emitted by that target. And from that, you can understand the elemental composition of that rock. So this is very standard technique now. This is called standoff detection because it is done from some distance. This is, of course, fusion, that is at much higher powers. So when you come to these intensities, there are there's a time scale as well as there's an intensity scale. So from this graph, one can see that different things happen at different times. So this is nanosecond, picosecond, femtosecond. This is 10 to the power 10 watts per centimeter square, 10 to the power 14 watts per centimeter square. Different things happen here. And so depending on what kind of an experimental system you have, you can address all those different phenomena. So this is the experimental setup in the lab. Basically, there is a laser beam. It can be a nanosecond pulse, it can be a femtosecond pulse, depending on which laser we use. And it goes to the target in the vacuum chamber. The good thing is, because it's a vacuum chamber, we can control the pressure, the ambient pressure there. And, the plasma is formed. Some target will be, mostly a metal, will be kept there. The laser beam falls on it, plasma is generated. Now you study that plasma. You can do that spectroscopically if you have a spectrometer. You can do that electrically if you have a Langmuir probe, for example. So all that is possible. So in our setup, this is how we actually detect this. The spectrometer is here. It has a CCD as well as a PMT. The photomultiplier tube is useful for giving us temporal information, what happens in time. The CCD is good to get the spectrum of emission. So we can do them both. And this is basically what it is. So this is the experimental setup in real. This is how it looks in reality. So this vacuum chamber, which we use these days, was given by Jindo from IPR. So eventually Jindo said, it's okay, you can take it. No need, because first we took it only as a loan for some time, but then it was yielding us very good results, and then finally he gave it to us. So that, and here are the spectrometers and all that. So here you can see the plasma in this is how it looks. So, and here is the spectrum of carbon. Now, a lot of work in the plasma front was done by Smijesh. And so this is the emission from the zinc plasma. So you can look at the temporal behavior. You can try different pulse widths like 100 femtoseconds, 200 picoseconds, 10 nanoseconds. So you can see that when we use nanosecond pulses, the energy is more, and therefore it gets heated up more. You get a better plasma plume. And then you can measure how fast, because it moves forward. Once it is formed, it actually moves forward. So you can measure its velocity. All that is possible. You can calculate the electron temperature from plasma emission. Then there are ways of doing that. Number density can be calculated. So all those things were done, and after that, and published, many papers were published. And then interferometry can be used for the estimation of electron number density. That is possible. So this was done by Amok, Sebin, and Cyril. Shadowgraphy can be done. That is another way of actually measuring the movement, the motion of the plasma plume, how fast it goes. X-ray emission, Anija did way back in 2005, I think, right? So this is your data, isn't it? Right? Yeah. So I had to pull it out from, yeah, it could be done. Then surface structuring, I think I need to go fast now. So this was done by Nancy and with the strong support of Anoop. So this is the difference between nanosecond and femtosecond ablation. So femtosecond gives a much better ablation. So this was the setup. And Nancy, in fact, generated vortex beams which had orbital angular momentum by using a spiral faceplate. So this is what was done. And she could make very interesting structures of this kind. So this is, because it's like carving out something from a target, because your beam has orbital angular momentum. So you remove the stuff around, and in the center, it stays. So that's what was done. So like that, then you can make many patterns and all that. So this is a gold coating. It was done like that. And surface enhanced Raman scattering, we tried that also, but I don't think we got much of an enhancement. But there was some enhancement, but not like what is usually claimed in publication. Our setup was not really fit for that. That's what we understood. I think that with that I will stop whatever scientific work that it's a very small cross section of what was done over 25 years. So there are so many people who contributed to these efforts in very many ways. I'm not saying that all these people can be seen in this slide. There are even more people. But these are the photos I could manage to get in a very short time. And there are many other people. They all helped us in various ways. Either they gave us the samples, some of them, like Rita, was willing to calculate. So all those things happened, and our success was very much dependent on these people. So I should say that what I learned from these last 25 years of working in RRI is basically, even before, all my entire scientific career is that whatever modest success you may have, it is because of the ecosystem that you are in. And that ecosystem is composed of great institutions, great seniors, and great people. This not only includes your mentors, but also your mentees, whom you have mentored. This is what I learned. We need to have good students, good people, who are willing to work. So rather than getting an Einstein into the lab, I would rather prefer getting somebody who has that mentality to work hard. You may have to work up to, when I was a PhD student, we were all working at 2 o'clock in the morning and all that. In those days, I'm not saying that that should be replicated, but that mentality to work should be there. And with profound gratefulness to all the people I have now moved on to another position from RRI. And I thank everybody who was with me in this journey. And I have to acknowledge many people separately. So that includes RRI directors, Professors N. Kumar, Devi Subramanian, and Tarun Sauradeep for all the support they gave me. Faculty colleagues in the committees, again, admission and coursework committees, other committees, even in other ways, like you just go to the canteen for a cup of tea and you have some discussion. In many ways, faculty colleagues, in particular from Lady Dog College, Madurai, St. Joseph's College, Arun is here, CUSAT, admin colleagues, many of you are superb support. I have to really say that the support that we receive from the admin here is wonderful. So, Subbu in particular, with all the committees that we work together, Subbu was great. Everybody else. Students, postdocs, research assistants, visiting students. I happen to have a lot of visiting students and project students, research collaborators, industry colleagues. Without lasers, we cannot do any of these experiments. My lasers have been mostly from, I think all the pulse lasers were from laser spectra services, spectra physics lasers. So I thank them. Our mechanical services, Ibrahim and team and Suresh and team, Jacob and team, computer vision, Meena Sujada for electronics, E&B team for electrical, and they attend to the buildings, and engineers of the SEM central facility for all the measurements you did for us, all the RAM and FTIR, everything. Members of EEG, Rekhu is here, thank you. Rekunathan, Prabhu, other senior engineers, and all the other people in EEG have been very helpful, particularly in the coursework also, I should say that. Savida, Harini, Purnima, LAM secretaries, library staff, canteen staff, security staff. I don't know whether I missed out anybody. Even if I have missed out anybody, I thank them also from the bottom of my heart. Thank you very much.
I'd like to call Professor Tarun Sauradeep for giving the memento and thanking our Professor Reji Philip. So, yeah.
Thank you.
Microphone.
Okay, this was a amazingly rich talk, and I should mention that first time I really, when you come to a new institute, you're trying to get to know people. Amongst all the, there were a lot of people you had heard of already. Astro people, of course, I knew. Then there were very famous colleagues whom you hear of. Reji was a very quiet person, right? And the first time I realized what this guy is he gave, there was a school we started on practical electronics, and he gave a talk on the history of audio equipment. I was stunned. I was amazed that, here's a real guy who's hands-on and understands things at a level which, it's unique. I've always told him to go around, and I understand you already do that, but, I said this should be a talk given to every undergraduate place, because, you actually are describing things that they regularly use, but, never take the trouble to understand. So there is something, I thought, Reji, you have a uniqueness as a scientist, which is also very refreshing, because, India, we produce very patterned, science, and so, a particular pattern is good, particular pattern, but, this is unique that you stood out, and your history also tells me that, So thanks for narrating this amazing story, and I wish you all the best. On behalf of the entire RRI family, great time ahead, and I'm sure you'll, keep succeeding in whatever you do.
Thank you so much, Tarun.
And
Thanks a
on
lot.
behalf of the Raman Research Institute, I'd like to.